Let's let's quickly revisit the climate sensitivity again in this context. We already defined the climate sensitivity as the equilibrium temperature change you would get if when you increase the carbon dioxide to double the level at which you are presently and keep it there till all feedbacks have equilibrated. So delta T double CO2 is the resulting perturbation to radiation divided by lambda, which is obviously the feedback factor. The black body radiation, in other words, if you just had temperature adjustments to the increased radiation and the temperature increase resulted in sigma T to the fourth term, then that would be around 4 watts per meter squared for doubling CO2. Obviously, we have to add all the feedbacks. So in that case, you are writing the equilibrium delta T to doubling of CO2 as F times delta T0, where delta T0 is the change in temperature in the absence of feedbacks. For example, you would have to have atmospheric vapor, water vapor being constant. This is just a way of thinking with feedback, without feedback, because it's that gain factor that's very critical to understand the Earth system feedback. Okay, so the gain factor then is the equilibrium temperature you would reach after all the feedbacks have played out. The carbon has been taken up by the ocean, by the land vegetation, whatever remains in the atmosphere. Water vapor has responded, clouds, glaciers, and so on. So that difference of that equilibrium minus the change you would expect without any feedbacks divided by delta equilibrium. It's not one term, obviously we have multiple feedbacks. So this we can rearrange as delta T0 divided by 1 minus G. That's kind of the way electrical engineers manipulate things to look at the gain in the system. They are the ones which use the gain the most, but now in climate system we have to constantly worry about this as well. We've seen this already, where F is now 1 over 1 minus G, and G is the sum of GI, where we have many feedbacks in the system. So in this case, we have talked about carbon feedbacks in the last chapter. We will get into a little bit more detail here in terms of how the CO2 perturbation, let's say from anthropogenic emissions, kicks on a so-called carbon concentration carbon feedback. So it's about the system's response to increases in concentration and what are the climate feedbacks. Okay, there is a difference between them, even though they are intimately tied together. So the concentration carbon feedback basically results from uptake of carbon by land and ocean as a biogeochemical response to atmospheric CO2 concentration perturbation, which is what we are doing. And the climate carbon feedback results from the effect of climate change on carbon fluxes. So if you increase CO2, we are going to increase, obviously increase greenhouse gas effect and warm. For example, we're going to dry trees, and there could be wildfires which could get more intense and more frequent and longer, which we will see, which would further increase CO2 fluxes into the atmosphere. Whereas here you are going to increase the gradient of the CO2 between the, let's say, within the leaf and the atmosphere, and we will see that the difference between carbon CO2 inside and outside, as we saw in the last chapter briefly, is potentially going to drive enhanced uptake, but we will see what actually limits this so-called carbon fertilization. If it happened, then it would enhance the uptake. Also the same with the ocean. We will again look at that, and that will result in removal of CO2. So just remember that. And this paper by Gregory et al. In 2009 included the physical feedbacks as well as the carbon feedbacks that we mentioned. Concentration climate feedback, carbon feedback, which is negative because we expect this response, and the non-carbon response or the climate resistance response. You can think of that including all the negative feedbacks in the system. And you have certain positive feedbacks like the climate carbon feedback, heat uptake by the ocean and land, mostly by the ocean, is going to be a negative feedback. The water vapor and long wave processes, land processes are going to give you a positive feedback, and this is water vapor and lapse rate processes are going to give you positive feedback. Surface albedo is low, but it's potentially a positive feedback because more vegetation or desertification, more agriculture, glacier loss, all kinds of factors are going to play into these. So these are estimates. We will see that there are uncertainties in all of these, especially clouds. Here it is shown as a positive feedback, but it depends on which clouds are changing and whether they are going to allow more radiation to come in and block the outgoing long wave, or they're going to increase reflectivity and get rid of more solar radiation. Black body radiation is obviously negative because as you warm the atmosphere, sigma t to the fourth is going to be larger. So that's a direct negative feedback. Clearly the message, of course, always is that this black body radiation, which is always going to kick in, is not fast enough to keep up with the perturbations we are producing in terms of increased greenhouse gases. So in this case, the delta T equilibrium is a delta T0 without feedbacks divided by 1 plus the feedbacks or gains. So here you put plus, but some of them are positive and some of them are negative. So the amplification of the no feedback warming will depend on whether you have negative feedbacks or positive feedbacks overall. So these are the sums, and it's a ratio with respect to the black body radiation, which is the intrinsic negative feedback. So you can think that CO2 uptake is reduced by warming. There is evidence that land and ocean may be getting less efficient in taking up carbon. So is the greening of the earth really happening? We will see that those kinds of feedbacks leading to a faster growth rate in atmospheric CO2 concentration and amplified warming. So this is a nice way of unifying what typically we look at in terms of just the physical climate feedbacks by combining with the carbon cycle feedback, making a distinction between concentration carbon feedback and climate carbon feedback. Okay, so it's kind of a heuristic argument at this point, but let me just close this podcast by reminding ourselves that quantifying the feedbacks is not always easy at all, and measuring them directly is also almost impossible. Okay, think of things like ocean uptake. There are methane clathrates and permafrost and other land processes which affect carbon fluxes, albedos, carbon cycle, so concentration carbon and carbon climate feedbacks. They can increase greenhouse warming and CO2 formation from methane if there is a perturbation of these hydrates. We will see whether that's going to be a candidate in the 21st century, for example. You can also have increased warming of tundra surface and thawing the permafrost and releasing methane and CO2, which is also looked at already, and it's not so clear exactly what the feedback will be, because there are additional complications there as well, as I mentioned before, in terms of the thawed permafrost creating ponds which can have photosynthesis. Obviously at some point it might be a huge release of methane and carbon dioxide. So we have long wave cloud feedback and short wave cloud feedback. So it's about whether they are trapping more long wave than before because of the perturbation, or they are changing the short wave reaching the surface. And you can see that they are not uniform. At high latitudes where there is a net energy loss, there is a slight positive feedback. In the tropics, especially over the warm western Pacific, there is the deep convection happening, which seems to have positive feedback. But on the Indian Ocean side, maritime continent side, which is in the subsidence region and rainy region, well, Eastern Indian Ocean is not so rainy as the maritime continent, but you can see that it's the same with shortwave. Here you have positive long wave, negative short wave. The net cloud feedback is then kind of a mixed bag. At higher latitudes it's negative, in lower latitudes and over land it's positive. So these are estimated from satellite data, the best data we can get, and there are very nice studies on this. The question then is, how well are the models capturing these feedbacks? So yeah, we will look at more and more of these, and each time we will try to say how easy or how hard they are to estimate and how the models are doing them.